I don't think it's nerdy to play the hurdy-gurdy. Let's talk about uniform continuity. Well, before we can talk about uniform continuity, we better define it. A function is called uniformly continuous on the set A if, for any epsilon, there is some delta so that for any 2 points in A, if the distance between the x's is less than delta, then the distance between the corresponding f of x's is less than epsilon. Which does sound a lot like the definition of continuous, but there is a crucial difference between them. So, what does it mean to be continuous on a set A versus uniformly continuous on the set A? Continuous on A means for any x in A, you are continuous at x. Meaning, for any x in A, given any epsilon which is positive, there exists a delta which is positive so that if the distance between some other point and x is less than delta, then, and still positive, then the distance between f of x prime and f of x is less than epsilon. So this is just hacking through the epsilon delta definition of continuity at a point and applying the continuity at the point x to every point in A. Now let's take a look at what uniformly continuous on A is. For any epsilon which is positive, there exists a delta so that if the distance between 2 points, and I'll just use x prime and x again, if that distance is less than delta, then the distance between f of x prime and f of x is less than epsilon. So here's the difference. It's in the order in which the quantifiers appear. To be continuous on A, for any choice of x, there exists a and for any epsilon, there exists a corresponding delta. So first you say pick an x, pick an epsilon, then you get a delta. Here, given any epsilon, pick a delta so that for any 2 x's, such and such. In short, this says delta is chosen after epsilon and x. Here, delta is chosen after epsilon must apply to all x. In the set A, of course. That's the distinction. Continuous on a set means for every point and epsilon, you must be able to choose a delta. Uniform continuity on the set says for any epsilon, there is one delta that will work everywhere. Let's hack through this definition with a straightforward example to begin with. A linear function mx plus b is uniformly continuous on which set? The entire real number line. Suppose epsilon is positive, we need to find a delta that works regardless of x. If any 2 x's are within delta of one another, then the corresponding y values are within epsilon. There's 2 basic cases. If m equals 0, well then f of x is constant and there's not much to prove here. Delta is essentially irrelevant because for any 2 x values, f of x naught, f of x1, you get out the same constant. The distance between those is 0, which is automatically less than epsilon. So delta does not really come into play if you happen to have a constant function. But let's suppose m is not 0. Epsilon was already given to us. I'm going to pick delta to be epsilon over the absolute value of n. Then if I take any 2 x's I want so that the distance between them is less than delta, let's take a look at the distance between f of x naught and f of x1. F of x naught is mx naught plus b. F of x1 is mx1 plus b. Okay, the b's cancel out. I can factor the m out, leaving behind absolute value of m times the distance between x naught and x1. But we assumed the distance between x naught and x1 was less than epsilon over the absolute value of m, so those absolute value of m's cancel out, leaving behind just epsilon. Overall, assuming that x naught and x1 were within distance delta, I concluded that f of x naught and f of x1 were within distance epsilon. And that's it. That's the proof. The only reason we had to do this in 2 cases was because you didn't want to try to divide by m if m happens to be 0. But as we saw, m equals 0 means the function is constant, made it even easier. Delta was totally irrelevant. This does raise a question. Why would I bother defining something new if it was the same thing? Well, we've defined things multiply many times before, But yeah, it is going to be possible to be continuous and not uniformly continuous. Here's an example. The function x squared is not uniformly continuous on R. Remember, the definition of uniform continuity is applied to a specific set. So it's possible to be uniformly continuous on one set and not uniformly continuous on another. I'm claiming x squared is not uniformly continuous on the entire real number line. So what we need to show is that the definition of uniform continuity fails. Uniform continuity said, for any epsilon, there exists a delta such and such. Okay, I'm just observing that no matter what delta we happen to choose later on, if I happen to pick x1 to be equal to x0 minus half delta, then certainly the distance between them is less than delta. It's half delta. But if I plug these two values into f of x0 is x0 squared, f of x1 is x1 squared, but x1 was specifically x0 minus delta over 2. If you work through the arithmetic, the difference between f of x0 and f of x1 will be exactly delta x0 plus delta squared over 4. So regardless of epsilon, if I pick x0 to be at least as large as epsilon over delta, okay, then the distance between f of x0 minus f of x1 is delta x0 plus delta squared over 4, but since x0 was at least as large as epsilon over delta, delta x0 is bigger than epsilon. So the distance between f of x0 and f of x1 is larger than epsilon plus delta squared over 4. It's larger than epsilon. Okay, delta squared is definitely positive. So regardless of epsilon and regardless of delta, I can find 2 points, x0 and x1, whose distance is less than delta, but whose distance in the range is bigger than epsilon. So there certainly exists an epsilon which is positive. In fact, any positive epsilon will do. So that no matter what delta you pick, as long as it's positive, as long as x0 was bigger than epsilon over delta, then you can find an x0 and an x1 whose distance is less than delta, but whose distance in the range is bigger than epsilon. What we're exploiting here about the function x squared is that it goes up really fast. So here's the function y equals x squared. Pick epsilon. Now remember, epsilon has to do with what's going on in the range. So I'm going to say epsilon is this big. Okay. Then this is fixed. This is no longer changing. Now if delta is chosen to be, I don't know, this big down in the domain, can I find 2 points that are within this distance in the domain whose corresponding values in the range are further apart than the epsilon that was given? You know, sure, I can pick maybe this point here and this point here. That appears to be smaller than this distance down in the domain, but the distance up in the range looks to be bigger than this one I picked right here. But this has to be true for this one particular epsilon. It must be true for any delta. So what if I pick a new delta that's really, really, really small? Well, the graph of x squared is going up really, really fast. So eventually it's going up very, very quickly like this. So maybe if I move far enough out to the right, in other words, if x0 is at least as large as epsilon over delta, and since epsilon and delta are both positive, epsilon over delta is a certain real number, okay? I can certainly move out very, very far to the right to find 2 points very, very close in the domain, but whose corresponding points out in the range are pretty far apart because the function was going up so quickly. So since for some particular epsilon didn't really matter, okay, but it definitely exists. For some particular epsilon, there is no delta that works everywhere. Okay, there is no delta so that trapping points within distance delta in the domain forces being trapped within distance epsilon in the range. If I go further and further down the x-axis, further and further to the right, that tiny delta won't be enough to trap points in the range close to one another. So there's no delta that works everywhere. So I don't have uniform continuity on the real numbers, even though I do have continuity on the real numbers. This is just a polynomial. Yeah, it's continuous on the reals, meaning you do get this continuity property isolated at a point. If x is close to a, then f of x is close to f of a. But the manner in which I mean close says pick delta depending on where you are. If you're at the point A, that's going to influence how you choose the appropriate delta. So that delta close in the domain forces epsilon close in the range. So since that method of choosing delta depends on where you are, we don't call it uniform continuity. That is the distinction between continuous and uniformly continuous. Uniformly continuous, the same delta needs to work everywhere. However, while x squared is not uniformly continuous on the entire real number line, it is uniformly continuous on the interval from 1 to 2. So let's prove it. Okay, for any epsilon which is positive, we have to be able to pick a delta. So for any epsilon which is positive, I'm going to let delta be exactly epsilon over 4. If I take any 2 points in this interval, I need to show that this delta works everywhere. Well, since x0 and x1 are in between 1 and 2, the biggest their sum can possibly be is 4. We're also going to go ahead and assume that they are within distance delta of one another. So what happens when I look at f of x0 minus f of x1? That's x0 squared minus x1 squared, which can be factored as x0 plus x1 times x0 minus x1. Well, x0 plus x1 can't be any bigger than 4, and x0 minus x1 was assumed to be less than delta. And what's 4 delta? Epsilon. So as long as x0 and x1 are delta close in the domain, then f of x0 and f of x1 are epsilon close in the range. What was really crucial here compared to the previous example is that our domain didn't keep going down the x-axis. Okay? The way we violated uniform continuity on the entire real number line was to pick x0 to be really, really big. But here, I'm only looking between 1 and 2. So there's like a biggest choice I can make for the numbers, and that became quite crucial. So specifically, looking at a drawing. So here is the curve, y equals x squared, just going from x equals 1 to x equals 2. It doesn't matter how small you make your epsilon. Okay? This is only going up so fast at any particular point. So I can force a tiny choice of delta that works at the worst possible location, which in this case is over here. Okay, I just choose delta according to where it was changing the fastest. And that choice of delta will therefore work everywhere else as well. And since one choice of delta functioned just fine everywhere, we did get uniform continuity. And right, the delta we picked here, in a sense, was chosen to be the delta that worked at the worst possible place, which means in other places, maybe a larger delta would have been enough. So I don't have to find the delta that's as large as possible. We just need to find a delta that does work everywhere. Here are some sample problems. Okay, look at how we did the earlier examples. The proofs here are going to be fairly similar. X squared is not just uniformly continuous from 1 to 2, but on any compact interval. Root x is uniformly continuous from 1 to infinity, but not from 0 to 1. And if f of x is uniformly continuous on 2 sets, it is uniformly continuous on the union. So hopefully these videos have been helpful. If they have, go ahead and throw down a comment, subscribe to the channel. It helps me gauge how invested and involved people are. Okay, also hopefully we were able to work through these sample problems. Let's move on. Here's a small little theorem. If f is uniformly continuous on a set, and xn is a Cauchy sequence in that set, then f of xn is also Cauchy. Now remember that we've shown Cauchy sequences and converging sequences are the same thing. So the fact that this is phrased not about converging sequences, but rather about Cauchy sequences is really just there to suggest how it's going to be proved. Well, a Cauchy sequence does converge, so suppose its limit is x prime. Now we don't necessarily know that the limit x prime is in A, because I didn't assume A was closed. So it might not have all its limit points. I just assumed f was uniformly continuous on the set. So for any positive epsilon, since f is uniformly continuous, there is a choice of delta, so that for any 2 points in the domain whose distance is less than delta, the corresponding distance in the range is less than epsilon. Now I'm using uniform continuity on A. Xn is Cauchy, so I'm going to use that definition. There is some n so that past that point, the distance between any 2 points in the sequence is less than delta. Delta is a positive number, so I'm using it in the definition of Cauchy. Given any positive number, past a certain point, any 2 terms in the sequence are less than that far apart. So delta is positive, so past a certain point, call it capital N, any 2 terms in the sequence, the distance between them is less than delta. But now I have 2 points in the domain, xn and xm, whose distance is less than delta. Because the function's uniformly continuous, and we have delta and epsilon related as such above, since 2 points in the domain are delta close, it follows that their points in the range are epsilon close. So since f of xn and f of xm are guaranteed to be less than epsilon apart in the range past this index, that means f of xn is Cauchy. So since we got xn Cauchy implies f of xn Cauchy. That's the theorem. The utility of this proof, by the way, it is a lot easier to prove if you can assume that the limit point x prime is in A. So if we weren't just uniformly continuous on a set A, but on something like a compact set A, the proof would be marginally simpler. What's nice here is that we don't need the set A to be compact. Any set on which you're uniformly continuous has this property. Another little theorem that we're going to put together here, if f of x is uniformly continuous on a set A, which we are now going to assume is bounded, but still not assume is closed, then f of x must be bounded on A. We did show continuous functions have maxes and mins, that's true, on compact sets. And as I said, we're not assuming A is closed, only bounded. So let's suppose to the contrary that f is not bounded. Let's assume it's unbounded above. So we're going to construct a sequence of points in the set A as follows. Okay, since the set is not bounded above, I can find a point where the function is bigger than 0. Call that x0. I can then find a point where I'm bigger than f of x0, but specifically bigger than f of x0 plus 1. Call that point x1. Then I can find a point where I'm bigger than f of x1, but in fact bigger than f of x1 plus 1. Call that point x2, and so forth. So the next point in the sequence is chosen so that the function evaluates to be at least as large as the previous value plus 1. And since the function is unbounded above, there's no issue finding points where the function is very large. Pictorially, without drawing a picture of the function, here is our bounded set A. Okay. I can find a point x0 so that f of x0 is bigger than 0. But the function isn't bounded above, so I can find a point x1 so that this is not just a tiny bit bigger than f of x0, but it's actually 1 unit bigger. It's at least as large as f of x0 plus 1. But the function isn't bounded above, so I can find some point where this height is at least as large as f of x1 plus 1. Why am I including this plus 1 here? Now clearly what I'm getting are points in the range that are just increasing. But if all I knew was that it was increasing, it might have a limit, and I don't want it to have a finite limit. So I want it to not just be an increasing sequence in the range, I want it to be unbounded. So I need to add 1 every time to force that. Well, I mean, I need to add the same amount every time. It doesn't have to be 1. What I do want to point out is because we are always going up by at least 1, the distance between 2 points in the range is at least as large as the difference in their indices. Okay, every time I increase the index by 1, I increase my height by at least 1. So if I increase my index by 2, I've increased my index twice. I have increased the value in the range by at least 1 twice, so I've increased the value in the range by at least 2. If I increase the index by 3, I've increased the index 3 times, I've increased the value in the range by at least 3. That's what we're saying here. The difference between 2 points in the range is at least as large as the difference in their indices. F is uniformly continuous, however, that was our assumption. So provided that the distance from x minus y is less than delta, the distance between f of x and f of y is less than 1. This would have to hold for any positive epsilon. I'm just picking epsilon equals 1. For choosing epsilon equals 1, there is a delta, so that if the distance in the domain is less than delta, the corresponding distance in the range is less than 1. A was a bounded set, and I was generating the sequence xn, which must be bounded. Therefore, there is a converging subsequence, okay, by Bolzano-Weierstrass. Since xn is bounded, it has a converging subsequence. So this subsequence converges, but it doesn't have to converge to a point of A, but it does have to be a Cauchy sequence. So since xn is Cauchy and delta is positive, past a certain index, all terms of the sequence xn are within delta of one another. But because we're uniformly continuous, if all terms are within delta of one another, then f of those terms is within epsilon of one another, which, and remember, we chose epsilon to equal 1. But we can't have the distance between these terms being less than 1 from uniform continuity, and the distance between these terms being at least the difference between their indices, which we got from the function being unbounded. Okay, m minus n is a difference between two different integers. It's at least as big as 1, which contradicts the fact that the distance is less than 1. I can't have both. There's a contradiction generated by assuming the function was unbounded. But here's the real purpose in introducing this definition of uniform continuity. If a function is continuous on a compact set, then it is uniformly continuous on that set. The converse, by the way, is quite straightforward to prove. If you are uniformly continuous on a set, then you are continuous on a set, whether that set is compact or not. The proof is pretty easy. You can find it in a million different places. This direction, however, is more important for us. If you are continuous, not just on any set, but on a compact set, then you are uniformly continuous. The two definitions are not equivalent. We've seen examples where a function is continuous, but not uniformly continuous. For example, x squared is continuous on R, but not uniformly. We did that. However, if you're talking about a compact set, then the two definitions are in fact the same. So now let's assume to the contrary that f is not uniformly continuous. Okay, so the definition of uniform continuity was, for any epsilon which is positive, there exists a delta which is positive, such that for any 2 points, if the distance between them is less than delta in the domain, the corresponding distance in the range is less than epsilon. So the negation of that is, there exists an epsilon which is positive, so that for any delta which is positive, there exists 2 points in the domain, which are delta close in the domain and epsilon apart in the range. So if that works for any delta, let's use the sequence we use a bunch, 1 over n. So for each choice of delta equals 1 over n, there exist points x and yn in the domain which are delta close in the domain, but f of them is epsilon apart in the range. Now xn and yn are both drawn from the compact set A, but otherwise I really don't know what they're doing. But they are both bounded. So there's a subsequence of the xn which converges because of Bolzano-Weierstrass. If xn is bounded, it has a converging subsequence. Now, if I just look at the same subsequence of the yns, those might not converge. But the yns were bounded, and therefore this subsequence is bounded, so it has a subsequence which converges. So from the original sequence of xn's and yns, pass to a subsequence where the xn's converge. Now on this subsequence, pass to a new subsequence on which the yns also converge. So this is a subsequence drawn from a subsequence. But since the intermediate step had the xn's converging, and now I have a subsequence of that, the xn's are still converging to the same thing. So now what we have is a subsequence of a subsequence where the xn's and yns are both converging. Okay, but since our set was compact and we have converging sequences, they're converging to a point in that set. So the limit points x prime and y prime are in A as well. Also, the difference between xn and yn was less than 1 over n. So the sequence xn minus yn just flatly converges to 0. So any subsequence of it also converges to 0. In other words, xan minus yan also converges to 0, so the limit x prime and the limit y prime are distance 0 apart. So x prime must equal y prime. So we have a sequence xn, a sequence yn. By passing to a subsequence of a subsequence, we have the x's and y's converging to the same thing. This definitely contradicts our assumption that f of these points was always the same distance epsilon apart. Okay, remember, we've assumed we didn't have uniform continuity, so there existed an epsilon for which a bunch of stuff happened. This epsilon is not changing. So both sequences are converging to the same thing. The xn's are converging to x prime, the y's are converging to y prime, but x prime equals y prime. By continuity, if the xn's converge to x prime, the f of xn's converge to f of x prime. Since theyn's are converging to y prime, the f of yn's converge to f of y prime. But since x prime equals y prime, certainly f of x prime equals f of y prime. Therefore, we can't have this, okay? I can't have the distance between the x's and y's be epsilon apart all the time, but have them converge to the same thing. This doesn't seem like that hugely important of a result, I'll admit. It does show, for the one part, that uniform continuity and continuity are not equivalent. On compact sets, it is. Okay? If you're uniformly continuous on a set, you can always prove you're continuous on that set. If one delta works everywhere, then yes, you can find a delta at every x. So uniform continuity does imply continuity. It doesn't always go the other way. Okay? Continuity does not always imply uniform continuity, but it does on compact sets. So why is this so important? We'll see later on, is the best I can do for you. We're going to rely on this very strongly at one point further away in the course. But not right now. Okay, we're done for now with uniform continuity. That last result, that continuity on a compact set implies uniform continuity, remember it, we'll use it, but not yet. Anyway, come on back, we're going to start talking about derivatives soon.